student in computer science at the University of Maryland, advised by the Professor Bahar Asgari. His research focused on the efficient machine learning at the intersection of the computer architecture, large language model, and sparsity. His work has been accepted at the top machine learning and computer architecture videos, and he is currently research internship. He's doing a research internship at AMD, and one more thing, he's very good at basketball. So let's welcome the speaker.
Hello everyone, I'm Donghyeon from the University of Maryland, and I'm here to present my paper titled Coruscant, Co-designing GPU Kernel and Sparse Tensor Core to advocate on sparsity and efficient LLM inference. This work is done in collaboration with Helya Hosseini, Ramyad Hadidi, and Professor Bahar Asgari. Large language models are becoming increasingly larger and more complex, necessitating efficient inference. To tackle this challenge, several branches of model compression has been explored, namely model distillation, quantization, and pruning. Compared to the other two methods, model pruning stands out as a less adopted technique. In this year alone, we saw model distillation actively used in DeepSeek R1 models and GPT-OSS providing forward quantization out of the box. We attribute this lack of popularity in model pruning to its nature, which, unlike distillation and quantization, induces sparsity in model weights that is difficult to map efficiently onto model compute hardware. To achieve compute efficiently, pruning must often impose structured sparsity patterns on the weight matrices. So let's take a closer look. Structured pruning moves entire rows, columns, or channels, making it easy to map onto existing hardware as a smaller dense matrix. But it's rigid and often leads to accuracy degradation as a byproduct of a pruning algorithm, moving a larger variety of elements. Unstructured pruning, on the other hand, allows pruning to happen at the finer granularity, but often comes with the challenge that modern hardware, including GPUs, can't efficiently exploit it. It must be computed as dense. And thus, most current pruning methods instead adopt semi-structured sparsity to map to supported architectures, such as the two-front pattern using modern GPUs sparse matrix compute units, where every two non-zero must exist among 4 consecutive elements. And thus we have a conflicting trade-off along the axis of sparsity patterns. More rigid the structure, more efficient is the hardware mapping at the cost of model accuracy. Freedom on sparsity pattern, while better ascertaining model accuracy, sacrifices efficient hardware mapping. As shown in our comparison, imposing pattern constraints like 2-4, or even any other semi-structured variants, can increase accuracy degradation compared to unstructured pruning at the same sparsity ratio. And therefore, our goal is to bring back the benefits of unstructured pruning, but make it efficient to run on modern GPUs. What makes unstructured sparsity in LLM even more challenging is its unique moderately sparse sparsity range. Surveying a perplexity of several pruning methods across sparsity ratios, we found a distinct pattern in modern accuracy degradation. First, perplexity remains similar across 10 to 30% sparsity, and in this case, there's no reason not to use 30% sparsity. And second, perplexity degrades starting from 50% with significant degradation from 70% sparsity. And therefore, we focus on the sweet spot between 30 to 70% sparsity, which offers a strong balance between accuracy retention and potential for compression and acceleration. 70% sparsity was also included to be forward-facing for future pruning algorithms that may preserve model accuracy better. However, existing sparse formats like CSR and COO fail to efficiently represent matrices in this region. In the left figure, we show the compression ratio, which is the dense matrix size divided by the compressed sparse matrix size. And in our target sparsity range, existing sparse formats often become larger than the original dense matrix itself, as shown in the red region. This is explicitly due to representing the non-zero positions with numbers. Such was also the case for Flash-LLM, which was a previous state-of-the-art GPU kernel for sparse LLM inference that motivated Coruscant. Flash-LLM uses a 16-bit tau-wise offset per element. And as you can see from the figure on the right, on 50% sparsity, for example, prune non-zeros are simply replaced in terms of memory footprint by the non-zero positions and thus no compression at all. This was effective for Flash-LLM as it targeted sparsity above 70%, but from the previous slide we saw that on that high of a sparsity range, the model suffers from significant accuracy degradation. And this observation motivated the core design of Coruscant, where a bitmap-based representation of non-zero positions can effectively compress unstructured sparse matrices in our target sparsity range. And thus, we start with our first contribution, the Coruscant bitmap-based sparse format. As seen on the figure on the right, each tile contains at max 64 non-zeros, represented by a 64-bit bitmap and the corresponding tile offset, which points to the start of the tile's non-zero. Our format is designed with GPU kernel and architecture into consideration. As two tiles are each mapped to a single warp thread, the tile size of 64 allows a bitmap tile to be represented as a single 64-bit integer, as well as fed into the GPU register file. Column-wise styling was selected to avoid shared memory bank conflicts during the decompression stage, later explained in the GPU kernel section. And as elaborated in the previous slide, bitmap drastically improves compression efficiency, and we leverage this to accelerate memory-bound operations in LLM inference, as well as reduce global memory consumption. And now we move on to the second contribution of Coruscant, the GPU kernel. When profiling LLM inference on Llama 2 7 billion and 13 billion, we find that decode phase dominates the total execution time. And among the decode phase, rate projection operation, now SpMM, due to prune rates, is dominant. And also, as the batch dimension is significantly smaller than other dimensions, these SpMMs become skinny and therefore memory bound. And thus, our goal is to reduce global memory footprint and bandwidth demands by keeping operands compressed as long as possible, all the way from the GPU global memory to the GPU processors. In roofline analysis, this is represented by a rightward shift caused by increased operational intensity. Leading to the second contribution, which is the Coruscant GPU SpMM kernel, which fully leverages our sparse format to achieve this. It follows the load as compressed and compute as dense strategy of Flash-LLM, but optimized for our target sparsity range using our bitmap-based format and decompression algorithm. So here's the process. First, the compressed tiles of the sparse weight matrix are loaded from the global memory directly into the GPU registers, as shown in the red box, the GMM2 regs. Then each thread decompresses its assigned column tiles into shared memory using a bitmap decoding algorithm. Second, in the next iteration, tensor cores then perform matrix multiplication as dense on these decompressed tiles, loading them from shared memory and doing computation. To maximize utilization, we use the shared memory as a ping-pong buffer to overlap two concurrent loads and computes. The detailed descriptions can be found in both the paper and our GitHub repository. We also tailor custom decompression loop using the CLZ instructions to find the set bits quickly. Each warp thread performs this decompression algorithm on two consecutive 64 element tiles. And as each thread decompresses its unique non-zero tiles, the divergent nature of decompression often causes the CUDA compiler to spill the non-zero tiles to the local memory, despite there being enough registers. And by keeping this loop iteration static, as shown in the red box, we can avoid this and use maximum registers as possible. Also, an important part of the kernel design is how we avoid shared memory bank conflicts. As each processor of our GPU contains 32 banks of shared memory, each 4 bytes wide, if multiple threads try to write to the same shared memory bank during decompression, performance drops due to serialization. To prevent this, Coruscant uses a column-wise tiling, where each thread is assigned to 2 columns, ensuring that each thread does write to distinct shared memory banks, avoiding conflict-free writes and better utilization. Our third contribution loops one step further, modifying the tensor core architecture itself. Even though the Coruscant kernel reduces memory transfer, it still needs to decompress each tile in software before feeding it to tensor cores. And we analyzed that this is up to 36% of total execution time. Revisiting the load and compute pipeline, where bitmap compression reduces the global memory to register data transfer, as seen in the GMM2 regs, Decompression on the kernel level adds additional latency to each iteration, as shown in the red boxes. To remove this overhead, we propose a Coruscant Sparse Tensor Core, which integrates a lightweight bitmap decoder inside the Tensor Core pipeline. This unit directly reads compressed tiles from registers, then decode the bitmaps on the fly, and feeding the valid operands to the multiplier array, eliminating the shared memory decompression stage from the kernel side. We build on top of a previous NVIDIA Tensor Core model of a previous work by Donghyeon et al., which interprets Tensor Cores as thread-level MAC lanes with operand sharing, executing a fixed number of multiplication and accumulation per cycles. Our bitmap decoder is inserted as a combinatorial circuit before this MAC lanes to operate at a thread level, reusing existing MAC lanes and accumulation trees. Additional details in the bitmap decoder internals, as well as the formulation change in the MMA instruction dimensions, can be found in the paper. And this is our evaluation methodology. We evaluate both the kernel and the sparse tensor core on our NVIDIA 6000 Beta GPUs. Notably, we model the sparse tensor core's behavior as a real kernel that runs on a system GPU, similar to the modeling methodology of vector sparse. We do this from the fact that Coruscant Sparse Tensor Core bitmap decoder is combinatorial, and therefore sparse MMA also runs at the same number of cycles as a dense MMA would. And therefore it can be used in the place of unstructured SPMM instructions right after the compressed non-zero tiles and bitmaps are loaded to the processor's registers file. We measure metrics in two categories, efficiency metrics and LLM quality metrics. For workflows, we use OPT models for SPMM kernel evaluation and Llama models for end-to-end inference. Now let's look at the results. First, Coruscant kernel, which can run on any commercial GPUs without architecture modification, outperforms both dense and sparse baselines across our target sparsity. For dense state-of-the-art cuBLAS, we achieve 1.09 speedup at 30% sparsity, the densest of our target range, and up to 2x speedup at 70% sparsity, with speedup increasing the sparser range. For sparse sort of Flash-LLM, we achieve 1.05 speedup at the highest sparsity to 70%, and up to 1.4x speedup at 30%, the densest. And with the Tensor Core design removing software decompression overhead, we see that the Coruscant Sparse Tensor Core and kernel combined achieves an additional 1.3x speedup over the Coruscant kernel. By removing the decompression latency from each pipeline iteration, we observe an increase in Tensor Core utilization. And by reducing register shared memory decompression, we also see reduction in shared memory stalls. So encompassing both the Coruscant kernel and sparse tensor core, the primary speedup by using a bitmap compression to reduce the data transfer from GPU global memory to each processor. And revisiting our roofline, the entirety of Coruscant can be interpreted as a two-step optimization, where the bitmap decompression represents a rightward movement through the increase of operational intensity, and a vertical upward movement signifying the increased throughput by removing the decompression latency. For end-to-end inference, we see increase in token generation throughput in both Llama 2 7 billion and 13 billion models. Notably, as can be seen on the Llama 13 billion side, using Coruscant's compressed weights reduces the memory consumption in the global memory, allowing larger batch sizes. This additionally increases token generation throughput as compared to a dense inference that's limited to a smaller batch size. And also, please refer to our paper for additional numbers and analysis on latency, power, and area comparison with previous sparse tensor core designs. Sparsity exploitation characteristics, where we think about if we need to leverage sparsity for compute skipping or compression, which leads to comparison between Coruscant to the cuSparse LT's 2-4 semi-structured sparsity kernel, and also with different end-to-end semi-structured accelerator variants. We also do performance on different workloads, mainly summarization, conversational, and reasoning, which differs in terms of input to output token ratio, so larger prefill versus larger decode. And also the impact of compressing the weight transfer over the PCI Express, and more. So to conclude, Coruscant is a co-design of GPU Kernel and Sparse Tensor Core aimed at accelerating memory-bound SPMMs of LLM inference by reducing data movement. To address this, Coruscant introduces a bitmap-based sparse format that compresses 30 to 70% sparse matrix efficiently. We design a GPU kernel that leverages this format to reduce data movement while maintaining high tensor core utilization. And finally, with a minimal hardware modification, the bitmap decoder, Coruscant Sparse Tensor Core eliminates decompression overhead, achieving up to 1.75x speedup over cuBLAS. And together, these motivations bridge the gap between the algorithmic unstructured sparsity and hardware efficiency, paving the way for faster and more memory-efficient LLM inference on the future GPUs. Thank you, and we're happy to take questions and comments.
Thank you, Stephen. If you have a question, come in front and come close to the microphone and ask your question. Okay, I have a question. So the prior work has proposed a lot of the multi-compression techniques. So how feasible is your idea for it, like with an unstructured sparsity in your idea in quantized model?
So quantized models have a different challenge in that we are able to do this on a FP16 16-bit matrices, because removing a 16-bit element and replacing that with the bit-level position elements yields a higher compression ratio. As the actual numbers get smaller bit width, the compression ratio does become a lot harder to maintain with the bitmap level of non-zero position representation. So I think it will work until like 8-bit, but I can't say sure for 4-bit quantizations.
Oh, I see. Any other questions? Okay, from my side, I have a last question. So you focus on the weights, right? While the KB cache is the critical structure, if you want to know. Does your work, does your idea work for the KB cache as well?
So KB cache is a different challenge because one, there isn't a lot of ML works that actually does unstructured pruning on KB cache. It's ideally because because KB cache is generated during inference, you would have to prune and compress during runtime. Although decode attention is basically matched as PNVs, so they would be memory bound significantly. We actually explore that in our next paper, which is Mustafa, which is the feature on NERVS 25. So if you're interested, please take a look at that paper.
Okay, we can talk about that later on. Okay, let's take this to the last speaker once again. And this is our session 2A. Thank you for attending this session. And now, enjoy your lunch. Thank you.